Thank you for joining the first edition of our Storlytics Depth of Charge Talks webinar series. This one is called Designing Utility Scale BESS for the Grid of Tomorrow. Our first speaker, Dr. Marek Kubik, is with us here. He's a leading expert in battery storage with more than 17 years of experience in grid scale energy storage deployment. Earlier in his career, Marek was part of the founding team at Fluence, where he helped scale the company into one of the world's largest and leading energy storage technology providers. He also supported the development of multi-billion-dollar BESS platforms globally. His experience spans the full life cycle of energy storage, from early first-of-a-kind projects and technology evaluation to large-scale deployment, commercialization, and infrastructure investment. Marek is also a Storlytics luminary, working with us closely to advance energy storage modeling. We also have Christian Ward, who is a battery storage engineer at Southern Company. Now, for our international attendees, Southern Company is a leading U.S. utility in the Southeast with over 50 gigawatt hours of planned BESS projects by 2035. Christian works within the Technical Shared Services Organization, leading efforts in BESS procurement, BESS OEM and integrator evaluation, performing modeling, and the development of renewable engineering standards. He holds a double major in chemical engineering and chemistry from the University of Alabama. Christian's experience with large-scale battery systems and the Storlytics modeling platform has helped him shape how utilities evaluate warranties, forecast battery state of health, and assess long-term performance. Also have Dr. Vikash Venkataramana, and I apologize for that. Vikash leads the ESS business at Amara Raja, bringing deep expertise in technology commercialization and product leadership across renewable energy and energy storage. He has a proven track record of scaling new technologies and building business at both startups and global organizations, including leadership roles at Goshen, Rept, Jinko Solar, Enervenue, and Hanwha Q-Cells. Vikash holds a PhD in applied physics, a master's degree in nanoscale science and technology, and an MBA from the University of Texas. And last but certainly not least, John is the head of energy storage and emerging markets at Camelot Energy Group, bringing deep cross-disciplinary experience across the full energy storage project lifecycle. He has held leadership and technical roles spanning utilities, EPC finance, asset management, project development, and product development at organizations including Tata Power, Mortenson Construction, Sonova, Pine Gate Renewables, and Vestion. Raafe has contributed to more than 5 gigawatt of operating wind, solar, and storage projects, and over 25 gigawatt hours of storage deployed across the U.S. He holds a bachelor's degree in electrical and electronics engineering and a master's degree in energy science, technology, and public policy from Carnegie Mellon University. So that's it for our kind of guest panelists here in this webinar. As for me, I'm Sherif Abdelrazek. I'll be serving as the panel moderator for today's panel. I'm also as co-founding CEO of Storlytics Energy Storage. With me here is my trusted partner, Jakir Hossain. He'll be one of the panelists in the panel today, and he is the co-founding Chief Technology Officer within Storlytics. All right, shifting to the first portion of our webinar here, we'll be jumping into a presentation from Christian Ward. Christian, I'll pass it over to you if you want to share your screen and dig into the presentation.
Thank you for the intro and for everybody joining today. So I want to start by acknowledging something about the people here in this webinar today from all across the world. So we've got asset managers, engineers, procurement professionals, planning and development teams, and every one of you is wrestling with some version of the same question. So if you're in asset management, You're looking at your operating fleet and you're asking how long before I need to augment. And if you're in planning and development, you're asking how do I size and structure these projects, knowing that the rules are changing faster than the contracts can keep up. So my name is Christian Ward, and I come at this from an owner-operator perspective. I've been directly involved in deploying, operating, and augmenting battery energy storage systems at Southern Company. So everything I'm going to walk you through today comes from real operational experience, including the surprises, the setbacks, and even the moments where the plan met reality and we had to adapt. So let's start where every life cycle decision begins, how you evaluate the technology you're buying, and more importantly, how you keep evaluating it long after the ink is dry in the contract. So we have these three pillars of evaluation. First, the technical performance when you're comparing vendors during procurement. You're looking at proposals. And then here's the issue with that. When you get different proposals from different vendors, those proposals rarely use the same test conditions. Some vendors propose an energy storage solution of thermal oxaloads in Atlanta, Georgia. Some do standard operating conditions at 25 degrees C. And so part of my job and my team's job is to normalize those vendor claims so you can actually understand what you're getting from each vendor. Then the second pillar, your commercial and warranties. So warranty structures that might look strong on paper can have throughput limits that don't actually match your dispatch profile. And you might have a warranty that guarantees capacity for 10 years, but what if you're cycling harder than that baseline assumption? And the third pillar, this one has been rapidly forcing everyone's hand in the energy storage market as it's the supply chain risk. You look at manufacturing locations and fiat compliance, and risk is no longer something you manage at milestones. You have to manage it continuously as this market begins to evolve. So I'm planting a seed here that I'll come back to later in the presentation. And now we have this evaluation framework becomes critical when you look at where the industry is heading. So the industry is moving from 2 to 4 hour duration to 6 to 8 hour duration with 15 to 20 asset lives to now 25-year asset lives. And so that might sound like a straightforward scaling exercise, but trust me, it isn't. When you extend duration, extend asset life, simultaneously you add complexity. You compound that complexity. And that compounding effect touches everything. So your degradation modeling, your augmentation planning, your vendor strategy, your financial projections. And if your lifecycle management was fit for this paradigm on the left, it's going to fall short in the future. So the question becomes, if the horizon is longer and the risk compound, how do you plan for that from day one? And that's where the overbuild strategy is. So I'll talk about the overbuild strategy we use at Southern Company. So we took the approach to deliberately overbuild from anywhere from 3 to 5 years and take a 3-step or 3-pillared approach with overbuilding at deployment. It's a calculated decision based on your degradation projections, your commercial obligations, and that number of years of headroom you want for that specific project before that first augmentation event. And then step 2, you monitor and calibrate these systems. So once the system is operating, you take real field data and compare it against your degradation projections. And then step 3, you're augmenting at data-driven triggers. When the data tells it's time to augment, we're ready. And so we treat augmentation as a planned capital event instead of guessing in the wind. So that's the theory. Now, let me show you what this actually looks like when the plan meets reality, including the parts where we were navigating without a map. And I want to shift from this framework to a real story. And I want to be honest with you and everybody here in this webinar today about what went well and what we struggle with, because I think that's where the real value is for everyone here. So what in this chart is the example data from a real site. So we had our first augmentation at year 2, where we integrated new modules with the existing system architecture. So the same technology, the same vendor. And then at year 4, our landscape changed. Our OEM went bankrupt and it completely changed how we had to think about the future of that site. So overnight, the assumptions underneath every plan we built were in question. So spare parts and replacement modules, disrupted technical support, firmware updates, the technology roadmap we were planning for, and even our next augmentation cycle, all of it was gone. And so this is the situation where our asset managers were facing in one of our opcos. So this is where they asked me to step in and help them navigate what I can only describe as uncharted territory. So our asset managers began to ask some of these three critical questions. First, what is our true capacity? Not the nameplate number, not the number the vendors tell you, but the actual real world energy capacity of the system at any point in its life, according for everything that's happened to it operationally. According to, assuming your COD implementation and your augmentation events, how much energy do you actually have in your system when you apply for the degradation and account for adding additional modules? And so the second question was, when do we need to augment next? As you see here, our fourth year is coming close to that POI target. So how much time do we actually buy before our next augmentation? Do we have 6 months, a year, 2 years? And then when do we need to augment next? Or how much do we need to augment? So how many battery modules do we need? Since the sourcing has been disrupted, can we find additional modules from the same OEM? Do we have to look at additional modules from a different OEM, different system architecture? So those questions are exactly what I was responsible for answering. And the goal was straightforward: validate the model against what we already measured in these 4 years, then use that validated model to project forward with confidence. And what you're looking at in this slide is the result. So the chart shows both the raw capacity test data in green and the simulation model overlay. And the key thing I want you to see here is how closely the model tracks against actual measured performance. And so once we have that validation, those three questions from the previous slide were answered. So we could see our true capacity trajectory, not just where we were today, but where we were headed over the next several years with a confidence level we didn't have before. So the model gave us a projected augmentation window, not a vague sometime in the next few years, but a plan but a range we could actually plan against. So this is the shift I want everyone to take away from this webinar or this presentation. We went from looking in the rearview mirror with capacity tests to looking through the windshield with a validated simulation. And the capacity tests tell you where you've been, and the calibrated model tells you where you're going. And I want to emphasize something important here. I'm not here to pitch Storlytics or a software product. I'm telling you about an engineering decision we made as asset operators. So we needed better forecasting intelligence, and we evaluated the tools available on the market. And then we chose one that we could validate against our own field data. And the point here isn't the tool. The point is the approach. Measure, validate, model, and plan. And I also want to be transparent here. When you're looking at this Storlytics POI, it assumes a full depth of discharge of 0 to 100% SOC across the asset's life. So 365 days for 10 years in this chart. And as your battery storage doesn't operate like that, you have some outage events. Your market might not even assume, or it might not even utilize the full range of the SOC and do that depth of discharge at that 100%. And I also want to give a tidbit to the audience. So I've applied this same simulation, Storlytics modeling, to a different OEM, which has a different energy retention curve, which has different modules, different energy capacity, and a different site conditions, different POI, different energy, different power conditions. And what I was able to do is utilize our pit dispatch POI profile over the years. So the timestamp and the real power use, and even now the power factor, right? And so when we had this implementation of dispatching our own POI profile, we've had results of less than 0.1% difference between Storlytics and our capacity test. And let me pivot a little bit and answer probably some of the questions you all have in the crowd today. What did you need to do this? So on the left, you can see the simulation inputs, all that feeds into the model. And then on the right is what I'd like to call a proactive planning framework. So it allowed us for timing flexibility, increased engineering quality, because you're now making an engineering decision. You're not just accepting what ships the fastest. And it gave us a procurement advantage. So you're negotiating from a position of knowledge, not desperation. You know exactly what you need and when you need it. And that leverage directly translates into better pricing and better terms. So the bottom line of this slide is the transformation from reactive to proactive, converting future uncertainty into a planned capital event with a defined timeline, a competitive procurement, and proper engineering. So I want to end this today with 4 key principles, and these 4 principles I take into any new BESS project. So the first takeaway, overbuild is lifecycle cost optimization. So as we learned today, the unexpected will happen. That overbuild isn't an expense. You can think of it as an insurance policy that also earns a return through better procurement, better engineering, and avoided emergency mobilization. And then our second takeaway, vendor risk doesn't end at procurement. In such a rapidly changing world and industry, the vendor landscape can shift at any point, especially when we begin to plan for 25-year assets. And the third key takeaway, calibrated simulation converts reacting into planning. So degradation modeling validated against real field data transforms augmentation from an emergency response into a planned capital event. It answers the 3 hardest questions in lifecycle management. What's my true capacity? When do I augment? And how much? With a level of confidence you cannot get from capacity test alone. And the fourth takeaway, the duration shift compounds everything. So moving to long duration energy storage to 6 to 8 hour systems with 25-year asset lives amplify every life cycle challenge. So the degradation is harder to model, the technology risk is greater, the augmentation decisions are more complex, and the financial stakes are higher. So if your life cycle management framework was built for the old paradigm, it needs to evolve. And these aren't theoretical principles. These come from building, operating, augmenting, and troubleshooting real systems, and including navigating situations that no one has written a playbook for. So I hope this gave you a useful framework as you navigate your own projects, and I'm happy to take any questions, and I'd welcome the chance to connect afterward if any of this resonates with what you're seeing in your own portfolios. So thank you.
Really great presentation, Christian. And I'll ask you to continue to share your screen because we have a couple of questions here. First of all, it's really valuable to get that actual execution knowledge, right? There's a lot of projects being built today. Not a lot of people who have been involved in actually operating these projects have witnessed what actually happened. Really appreciate you conveying that to the audience here. Now, Naveed Rabbani, he posed a really good point, and I'll pose it to you as a question. So basically, he's conveying that a model is only as good as the type of data used to build it. A model used for a certain type of chemistry will vary across chemistries, make beside different environmental and usage conditions. So basically, what he's saying is, unless you're accounting for the type of battery cell, the chemistry, the environmental conditions like temperature, ambient temperature, and so on, and type of cycles, a model wouldn't really serve you good. So how has Southern been able to deal with that variability in operation conditions?
Yes, so we've been able to deal with it multiple ways. So really a lot of this starts at the procurement now that we do. So we ask vendors to provide a framework for their auxiliary modeling. So what we expect at 25 degrees C, what we expect at 40 degrees C, or even their minimum operating conditions, So we take that data and we utilize that within Storlytics to validate it and look at it. And then Storlytics has the ability to add your own meteorological profiles, and then it has already some custom set profiles as well. And as far as understanding how you can get the energy retention curves that the vendor provides, and you can utilize Storlytics as well to match those energy retention curves. So I'm talking about root mean square of, or our squared values of 0.99. So they pretty much model the vendor's OEM curves and what they do in these service purchase agreements or LTSAs or just your contracts in general. So hope that was able to answer the question.
Perfect. Thanks, Chris. All right, now shift to another question here. BESS is a total system that has battery, PCS, EMS. How are each component evolving and changing over time? Now, I'm not sure if that question is referring to how models of these components are evolving or accounted for in what Christian just presented. But Christian, I'll pass that over to you. Do you want to comment on that one?
Yeah, I can comment on it. How are these
clarified? He's talking about cost and technology wise.
Yes. So for the batteries are increasing their form factor. They're having increased energy capacity. So now they have an increase in thermal load. So that's when it comes into understanding your round trip efficiency. I see that also in the chat. So as batteries increase in size, they have increased thermal loads, and you can model that. And then you can model each component of this in the total system. So you have the battery, the PCS, EMS, your medium voltage transformer, your DC lines. You can measure every single component of this system. And there's also customization you could do within the platform, right? Adding solar and D-tide, T-tide. So all of those components can be modeled in this software. You also can do it right in Excel sheet. But I think when you go back and forth between an Excel sheet, you're like, did I get this right? Where did I get this? And we do our own modeling with Excel in different softwares as well, as far as our electrical studies team that looks at some of this information as well. So it's a dual approach, but you can model the entire system. And then when it comes to cost, you can take those costs from these vendors and their proposals and then compare it to what they did previously. You can compare it to what the market has and what the projections are in the market. And then if you use the same vendor or have the same vendor in procurement stages, you can compare that cost to their previous product or the same product they're offering now. And you can also look at different things, how FIAC goes into this, your ITC tax credits, right? So how the evolving nature of the market kind of pushes these costs or changes these costs into different trajectories, depending on if it's the same sale and it's a foreign sale versus domestic sale. You can just do so many different comparisons between cost and technology by utilizing this platform and just in general. So hopefully that was able to answer your question.
And Kristen, another question here from Naveed. What is the frequency of capacity tests you recommend to avoid surprises? And you guys have a unique perspective because you've actually been operating a lot of projects. What's the best frequency of capacity tests?
I would say at a minimum a year. So in this slide here, or in the slide in my presentation, some of those were capacity tests dictated by the market. Some of those were capacity tests we had done after, for example, the augmentation, and we want to verify how much energy we have after the augmentation. So I would say there's minimum one, but rare in cases where you're doing capacity tests 3 to 4 times a year, or 2 to 4 times a year.
Kristen, thank you for this presentation. Really helpful. With that, I'll go ahead and take back the screen here. And we'll shift to the panel portion of the webinar. All right, first question here, I'll direct to Vika and Kristen. I think given their background, both would have a great perspective on it. How are major industry players like Southern Company and Amara Raja going about evaluating new battery and LDES technology and assessing suitability for existing and evolving grid needs? Christian, you mentioned in the beginning of your presentation that every battery OEM, every technology provider will give you the characteristics of their system, of their product at different conditions. Most commonly, the conditions that best suit their product, because obviously they want to sell more product and they want to make their product look the best. But as a purchaser, as a project owner, you have to have the capability to compare technologies and battery cells, even LDES systems, apples to apples. In that light, how have Southern Company and Amara Raja been approaching that type of evaluation? And Vikash, I'll go ahead and start with you. You've worked with Rept and our venue and just too many major companies. So your perspective, I think, is going to be great. Take it away.
Sure, yeah. Thank you so much for that. So to start with, I think the question really is, what is the application that this particular product is looking to target, right? Is it LDES? Is it shorter duration? Is it frequency response and so forth? In most cases, it's project economics, return on investment, and the calculation that needs to be done that evaluates to understand if that particular product meets those requirements. So that's on the financial side. But obviously, data shared by an OEM is data shared by the OEM, right? So in most cases, we request field data, some kind of experience with deployments, all of those pieces to show that whatever data or they're providing can be validated. Ideally, third-party data would be great. Most cases, they might not have that. So that's something we push for. The final piece is on the safety and compliance. There's always a check on track record on and so forth, especially from a safety perspective, be it in the factory, be it in the field. Understanding how these products are performed over time is really important. I think with technologies with LFP, they've built that track record already. But if it comes to more emerging technologies, like today we talked about sodium, we're talking about a lot of LDS options. The question is it there to prove that this particular product can last 20 years or 15 years or whatever it's warranted for, right? So that always is a discussion that comes up. Yeah, independent of that, I think even with today LFP, these larger format cells and getting into these larger form factors, there's a lot of unknown territory that some of these players are entering into, right? So the question is, does the life and degradation perform as it was with the standard 314 amp hour cells? So a whole bunch of questions come up, and typically from a risk perspective, we need to validate both from some amount of field validation to show that these are reliable, they perform as claimed, and so forth.
Very interesting. Christian, what's your take?
Yeah, so Vikash hit it right. Mentioned some of the same things that are important to a large-scale utility like Southern Company. So I would say some of the biggest things are that safety and compliance piece. So when it comes to looking at some of these new technologies like iron sodium, nickel hydride, we've got zinc halide, organic solid flow. So we were looking at those all on pilot projects. And so we have research and developers that are looking at these, and they're also working with EPRI to validate these and say if they're safe, say if they can comply with these, with our safety standards. And then just looking at, to translate those microgrids to large scale, transmission scale, long duration. And then even you mentioned the sodium ion. So very interesting or promising technology that can come out in the next couple of years. And for Southern Company, it's still, let's look at field data. I understand that in China, it's a very big market and utilized a lot, but still not used in the US. So we're a little hesitant when it comes to looking at sodium ion versus the traditional LFP cells. So a lot of it just comes from market confidence and then evaluating these on the research and development front.
Okay. Yep, absolutely. And since you mentioned sodium ion, yeah, we've been trying to work on ways to avoid the only way of evaluating new technology to be like an actual pilot, which actually, if you think about it, takes a lot of time, takes a lot of resources. I think the shortest pilot that we're aware of will take anywhere from 2.5 years to 4 years or so So for sodium ion batteries, we're currently working with Peak Energy to create a model for their technology that folks or utilities that are interested in piloting can actually use as a precursor to ensure that this technology performance meets the requirements of the use cases they're planning. Because every utility, every developer, there are different markets, different grid services, at the end, different dispatch for BESSes. And when you dispatch BESSes differently, the performance of each technology is different. You'd want to know before actually going into a pilot that this technology is actually appropriate for the handful of use cases that a utility or a developer has. More to come on that within the next couple of months, but we're really looking forward to it here. All right, I'll shift to the next question here. Now, in this panel, we're very lucky to have panelists heavily involved in mega projects all over the world. Marek is doing a lot of great projects in the Arabian region. He has a lot of experience developing projects in Europe as well. Raafe, he's with Camelot Energy. They're doing a lot of great work with developers and financiers across the US, evaluating a project in the US, and certainly Asia. Raja operating there and also in the US, as I understand. We're able to get a lot of good perspectives from all over the world here. So with that in mind, and this is for all the panelists here, what use cases are most prominent in the different regions we just discussed? Marek, I'll go ahead and start with you.
Yeah, thanks, Sherif. And I'll try and maybe wrap this into the previous question as well, because I think there's some relevant points that kind of link across these two questions. So I've worked pretty globally. I'm currently in Saudi Arabia, so I'm seeing a lot of what's going on in the Middle East region, but I've also been in Europe. And as you mentioned at the start, I've been in grid scale storage 17 years. And the first sort of thing to say is the evolution of use cases started very much in the high C rate, very short durations, right? 15-minute, 20-minute, 30-minute batteries. It grew to 1 hour, then 2 hours, 4 hours. And now we're seeing these increasingly longer duration systems. So the link I wanted to make to the previous topic about how do you evaluate LDES technologies is as the cost curve is coming down, longer and longer duration technology becomes more feasible and economic, especially with BESS, but obviously you have to evaluate other technologies. And that's opening up also other avenues for what you can do with storage. So we started out very early with just the frequency regulation, right? Really second to second balancing. That's often the place that most markets first opened with, simply because that's the only thing that was economical, right? It's not a service that power plants really like to provide because they're moving from optimal set points to ramp up and down. But what became very common in the US, this sort of peaker replacement use case, so running during the evening peak after the sun has gone down and the solar is not there, is where the Middle East region, for instance, has leapfrogged immediately too, right? So we've skipped this whole short duration piece straight into 4 or 5 hour systems because this solar duck curve is emerging very fast. So this sort of Middle East part of the world, it's very much driven by renewable adoption. So you have a lot of solar, and you actually have, because of the latitude, longitude, it's very consistent solar with very limited cloud interruption. So really you just have a day to night energy shifting problem. So it's one of the most fundamental use cases people think of with storage, but it used to be out of reach because of cost. But now we're starting to see the point where BESS is economic for, you can argue exactly where that frontier is. There are projects of 11.5 hours awarded to battery storage in places like Australia, 8 hours in Italy, in California. So it's starting to emerge. And that use case is also coupled in the Middle East region very much with what we call non-wires alternatives, which is if you're building a solar project in the middle of nowhere, and often it is in the desert, you've got to build a transmission line to that solar project. And if you size it to the peak of the solar, that line is underutilized and it costs millions of dollars per kilometer. But if you've got a battery in for shifting the solar day to night, you also have a battery that's there to basically act as a virtual transmission line to help optimize the utilization of that line, right? You store the excess power in the day, and then you run that power line essentially more optimally over time. So that's one of the biggest and most exciting areas that is emerging, I would say. And the Middle East is one of these areas of the world where you can actually have round the clock renewable power now with the cost of solar and the cost of BESS in the region competitively with thermal generation or with nuclear, but built much faster. So that to me is a really exciting area. It's not there in the sort of more, let's say, Dunkelflaut-led regions of the world. So if you try and do the same thing in my home country, the UK, or in Germany, you'll struggle to get to a capacity factor and like a baseload reliability level with solar and batteries. But this is one of the things that in this region of the world is really quite exciting. So I'll stop there so I don't go on too long.
Really great perspective. Raafe, I know you have a perspective on this. You've been working with a lot of developers in the US. What use cases are you seeing from developers and IPPs?
Of course, thanks, Sherif, for that. Yeah, similar to Merrick, I just want to fold in the previous discussion as well when it comes to LDES and new emerging technologies. LFP is the baseline and became the primary chemistry of choice for stationary applications in 2020, 2021. Prior to that, it was primarily NMC. As of today, just to put it in context, almost 3/4 of new global battery storage installations are LFP based. And so that should just give you a baseline of what emerging technologies have to do in order to become emergent, is that they're competing against the incumbent on efficiency, availability, bankability, amongst other things. So that would include technical parameters like cycle life modeling, calendar aging, temperature interaction. So if you're in a high temperature environment like the Middle East, you would likely see increased capacity fade via kind of electrode film growth and impedance rise, which is a pretty critical factor in kind of when you're modeling things out. And then, of course, you have your bankability filters, right? Lenders apply a hard requirement for OEM financial strength, ability to secure insurance, and demonstrated technology readiness and operational readiness before any chemistry advances past procurement screening. As Merrick made a good point about how batteries were initially used in early days for the 15, 30-minute, 45-minute, 1 hour duration kind of discharges, is because there was a price signal available in the form of ancillary services. Ancillary services have long been the go-to use case for battery storage because you had a very formidable price signal that allowed the battery to charge and discharge strategically in both day ahead and real time. And most of the batteries we see that are installed and operating are based on a price signal that already existed in the market. Whereas for LDES, that price signal is embedded in the aggregate. And we'll come to that in a minute. As far as new technology is concerned, of course, I'm personally super excited about seeing competition with other technologies. Sodium ion was name dropped a couple of times. I think there are other technologies as well that are highly promising. Of course, we don't want to get into death by pilot. That's always a way that some companies do end up doing too many pilots and not being able to get to that commercial readiness point. But talking about there are flow batteries, iron air, compressed air, etc., that are emerging technologies that will have to compete on not only price but also technical performance across a variety of use cases. Coming to the use cases for the US market, I want to zoom out for a second. So we had something called the Inflation Reduction Act, or the IRA as it's commonly called, that enacted a standalone storage investment tax credit under Section 48. Prior to that, in order for you to get a tax credit for storage, you have to be co-located with solar. But the IRA changed that, and now you can have grid-connected BESS that could charge from the grid and still be able to get the base 30% ITC with the adders for domestic content and energy community siting. Then in July of last year, the One Big Beautiful Bill, which largely spared battery storage from accelerated phase-outs. Battery storage has a longer run rate relative to solar and wind, with credits available until 2032. That is an investment signal. And it tells you that the US regulators see battery storage as a critical piece of the puzzle. And we then had guidance on FEOC and domestic content and how that will that also upended the way people think about procurement and whatnot. Putting all that into context, and you look at kind of revenue models, right? All of that is important because a battery can do a lot of things very well, but it cannot do everything at the same time. And so we have to be conscientious of how we're modeling battery storage for specific use cases, for actual operating conditions that are prevalent at the site, whether it's ambient temperature, whether it's higher humidity, altitude level. If you're at a higher altitude, the air is thinner, so you have to do that as well. I'll talk about a couple of markets that I see how things are trending. In California, for example, which sets the standard for the most part, resource adequacy contracts, or RA, comprise majority of BESS and revenue. These are long-term utility signed agreements that project finance can easily underwrite. And switching over to Texas or ERCOT, it's an energy-only market with no capacity mechanism. So it's a pure arbitrage on a 5-minute settlement period. And actually, despite not having a capacity construct, Texas actually became the largest US BESS market in 2024 with about a little over 4 gigawatts of installation and an average project duration of kind of 1.7 hours versus what we see as a 4-hour duration in California. In the Northeast, in PJM, the capacity market, or ICAP, combined with frequency regulation stacking, is where we see the market. Complex capacity performance rules require BESS to demonstrate year-round availability in order to capture those high capacity clearing prices and being able to participate in what has largely been a symmetric frequency regulation signal. And so one thing is unmistakable across these markets is that the use cases are similar but not the same. It requires a level of granular modeling in order to make sure that you can actually capture those revenue streams and model those in a very accurate way. I think Christian's your presentation hit the right notes. And as having been a developer in a past life, I certainly see that models can sometimes be directionally correct, can sometimes be either too conservative, too aggressive. Where I really see the value where in the modeling side of things is having a deep appreciation for the OEM technical documentation, understanding the ins and outs of that, where there are potential risk factors. It could be from BMS inaccuracy to DC balancing issues that we see in the field, and how are those kind of making their way into the risk profile of typical project financing. So that said, standalone BESS deal structures in 2025 were split nearly evenly between tax equity and kind of IRA transferability, which reflects BESS's higher merchant risk profile relative to solar or wind, which have typically longer term PPAs. And so BESS has a long runway. It has a very bright future in the US markets, both vertically integrated as well as wholesale markets. And despite having different revenue structures and across the markets, we certainly see BESS being there are very strong price signals and investment signals in place today that will help BESS be underwritten at scale across these different markets.
Yeah, the point you mentioned about the Northeast and kind of use cases there and ancillary services, of course, yeah, being able to model that on the revenue side, definitely very important. But what we've seen also be missed a lot in the way that kind of developers and financiers are evaluating these projects is evaluating the impact of these, in a lot of cases, fast ramping use cases from an impact on the battery system side. What does degradation from a use case or a signal like a frequency regulation signal, how does that differ from just your typical one deep discharge a day? And what we often see is that developers are always assuming one deep discharge a day, even if the project is planned to always be in an ancillary service that has more shallow cycles, and that kind of in a lot of scenarios inflates the projected cost of the battery system compared to what it actually is going to be. And it's mostly because OEMs are just currently providing sizing based on that discrete cycle count per day, and it's always a deep discharge in those cases, most prominently the one cycle per day deep discharge. But
Yeah, if I can add something real quick, if you just want to just add something real quick based on what you said, you're absolutely right. With ancillary services, we do see those frequent shallow discharges in order to capture those reg up and reg down revenues. And you're right. Warranty, the way batteries are warranted today is based on an aggregate of one cycle per day or 365 a year, right? And so the underlying assumption is that on a daily basis, with all things considered, you're probably close to that one cycle, one deep discharge a day. Whereas in reality, it could be a combination of a several shallow cycles that could potentially overshoot that number or undershoot it, and which would have a measurable impact on that degradation and the state of health of the battery, right?
so
And the question that needs to be asked is, how do those models get reflected in financial models?
yes.
Because there is that risk that needs to be translated into actual kind of dollars and cents so that underwriters can actually figure out how they value certain revenue streams, certain use cases in different markets and whatnot. Very point well taken, and something that certainly we should dive in as an industry.
Yeah, and I'll chime in here real quick just to piggyback on that point from Raafe. We just finished a study with Duke University, Nicholas School of Environment, really to quantify that impact, right? So in one case, you are making this very high level generic assumption, one cycle, 365 cycles a year. And what if how you really dispatch the battery? And what is the impact of that on degradation? And finally, when you look at it through the lens of internal rate of return, levered IRR, our studies show it can be as much as 3% difference. So you can actually gain 3% more levered IRR if you really take the use case into account. So that's quite a big of gain in terms of project return. So it's not trivial, it's not in decimal points, it's full 3% difference in IRR that you are leaving on the table if you're not optimizing against your use case.
Yeah, I'm looking forward to that, publishing that study and getting it out there. Some really great work by Duke University. All right, I'd be remiss if I went away from this question without touching on data center use cases. Kristen, obviously there's a lot of data centers coming into Southern Company's territory. Is Southern Company seeing any asset upgrade deferral use cases come about for battery systems, or what's that dynamic look like?
Yeah, I guess I can speak about it from multiple different angles, but from the transmission level, right, it's increasing transmission lines, making sure that these renewables that we have are starting to penetrate more into the Southeast are connected so you can utilize that energy across 3 states or multiple different states. And from a D-type perspective, when you're thinking about power plants behind the grid, so FERC just came out with an allowance for big tech data centers. Well, let me back up. This is talking about one of our operating companies and how they're thinking about battery storage and D-type applications for data centers. So FERC allowed big tech to plug in data centers behind the grid instead of going into the transmission queue and then going the traditional route. And so one of the things our operating companies is thinking through with a large big tech company is to create a data center or to create a power plant for their data center behind the grid. So that's utilizing BESS at the front end of the project because you can get battery storage quickly compared to traditional CC and CT plants. And then as you're building that CC and CT plant to eventually become the main energy producer for that power plant to have the data center load, that battery storage will then go into as I guess you could think of it many ways for transient loading of the battery of the data center, and then assisted with power quality issues, and then also backup power. So that battery storage plant is thought to be the beginning of the project. And then as you create your CC, your traditional power plant, then that battery storage goes to the backup power and then have use for fast response, power quality, And then also when we're thinking about a world of more sustainability, and as that's one of our priorities. So that's the way we're thinking about, or one of our operating companies is thinking about battery storage and D-type applications with data centers.
Perfect. Thank you, Christian. All right, now shifting to our next question here. Mainly, it's about BESS augmentation, and if you've been around the industry, it's one of those topics that hasn't been getting a lot of attention in kind of the past couple of years, but we've seen a lot of players recently, like Southern Company and other utilities, and some developers are starting to get more sophisticated with it, and that's why it's the topic of this question. I'll start off with Marek. Marek, what are your thoughts on different BESS augmentation topologies?
Yeah, so for those that aren't familiar, there's basically three different things you can do. There's maybe more ways you can subdivide it, but Christian mentioned one of them in the earlier introduction, which is overbuilding, and that's the simplest, right? You essentially install more batteries than you need so that you don't need to augment, or you can delay your augmentation. So if you have a 4-hour system, you might put in 20-25% more capacity. You have to pick what's your optimal number. There are some advantages to doing that. The first and foremost is it's very simple because you just do it as part of your upfront procurement. You could do it once for the lifetime of a project. So actually in the Middle East, it's quite common to augment upfront because you imagine these sites are quite remote and in the desert, it's not easy to get out to them again in 3 years or 5 years or whatever it is to come back and augment and add some capacity. The second is, we may get into it a little bit later, depending on the time, high temperature environments. Overbuilding reduces the C rate of your battery system, right? So the more batteries you put on the DC side, the less the batteries heat up. So if you're in a very hot climate, that brings you quite some advantages. And as I said, because it's simple, you then don't really have to worry about your future vendor selection or your topology. The cleverest one, and the one that often receives a lot of attention until you realize how complex it is, DC augmentation. And that's the idea of, oh, I'm going to be clever. I only need to add battery capacity because that's the thing that's degrading. I don't need more inverters. I don't need more transformers. I don't need more anything else. So adding just DC batteries, from a direct cost perspective, it is going to be the cheapest way to add capacity, because first of all, you're deferring adding these batteries until you need them into the future, and you expect they're going to get cheaper. And second is you're not having to buy any other equipment. The biggest drawback of that is it's complex. The new batteries are going to have a different state of health to the old batteries. It may even come from a different supplier, a different vendor. As Vikash talked about, the form factors are changing, so you might have even different battery cells in the future, maybe even different chemistries. We've also talked about LFP versus sodium ion. So you're upfront making an assumption that it's the same cell, the same form factor, and maybe even the same supplier, right? The biggest risk is you're locked into a particular supplier. It's relatively easy to do it if you're planning to stick with the same vendor later on, but what if they're not competitive in the future compared to supplier B or C? So that one's the most complex and probably the one we could unpack into a lot more detail, because there's a lot of different ways you can do it. There are things you can do, add DC-DC converters to make it simpler, but then that's adding more cost up front. Or you can just reshuffle things around, which gets very complicated and it's very time consuming and manual. The last one, which is the one I would usually recommend, or a combination of augmentation maybe overbuild and this, is AC augmentation, which is not the sexy one, because basically it's leaving some land aside, maybe leaving some spare breakers on the site, and that's about it. And then just plan that in 5 years, you're going to come back and add some more battery storage system. That's going to be the DC side and the PCS, so the AC side, and the MV transformer. So you're adding more cost in because you're procuring more equipment. But on the other hand, you can then just do a full vendor selection of whatever is the best technology at that time. And that might be a materially different inverter, a materially different product technology. We've seen, like in the last 2 years even, we've gone from 3 megawatt hour containers to 5 megawatt hours to 6.25. So the pace is extremely fast. So I don't really recommend anything else, because if you're looking at out 5+ years, it's almost certainly not even something you can imagine at the moment. So that's essentially the three main approaches and sort of considerations.
Yep. Yeah, really good point. And you've touched on some really important points that just when project planning for some reason just seemed to always be missed. When as you said, in financial models, when you look at it as, and we've seen plenty, DC augmentation looks the best, right? But when you actually start thinking about how it's actually going to be executed, it's just a very slim chance that it'll actually work out as planned, especially without DC-DC converters. We've seen a lot of integrators submit proposals assuming the DC rack shuffling, right? Which, for those of you that are not familiar with what this means, is it's basically taking all the old battery racks, putting them behind old inverters. That way you're not mixing degraded battery racks and new battery racks. But then even with that, there's just, let's just set aside the form factor issue and all, but just the assumption that somehow in the 3 years or so of operation of the system, that all the inverters and all the racks behind them operated in the exact same fashion. None of them were offline for a certain period of time. That's a very slim chance for anyone who's been involved with battery project operation. So definitely we're not big fans of that methodology. And DC converters, so a lot of products out there come with rack level DC converters on top of each rack or each group of racks, and heading in the opposite direction. The whole point of augmentation is that you're trying to reduce capital costs, but here you are adding more capital cost in doing that, and also adding losses. Like DC-DC converters are not 100% efficient, so you're taking a hit on energy losses for your project throughout its lifetime. But all right, perfect. Again, thanks, Marek, for that perspective. Turn over to you. Any perspective on different types of augmentation here?
I think, yeah, Marek did cover most of those. So I think one thing I want to touch upon is the future of augmentation, right? If you consider, as we enter into the future, we see these larger cells coming in, right? And looking at how you would look at augmentation, I think more and more you'd see with the newer, because with larger cells, the number of strings per container is going to be less, right? Because let's say you basically have a cell that's 1000 amp hour, right? So traditionally you might have had 12 strings per container, but they're probably going to drop down to 3 or 4, right? So that's a very different way to think about it. And also when you think about BMS and other use cases now, traditionally it was more passive, right? But today, if you lose a cell with a large cell, essentially your string is a much bigger string, right? Thinking through all that, I think understanding how you plan for the future of augmentation also becomes very interesting, right? Where now most likely your BMSs would have to go into more active balancing mode rather than passive to try to make sure that your string imbalance is reduced. And when you augment, maybe with active balancing, you get a better outcome with the performance over time as well. But today I'm in China and I'm seeing all the tech that's happening out here, right? I can definitely see a future where our traditional concept of having maybe 12 strings per container and all of these things are changing, right? So people are planning for the future of how BESSs are built and how they maintained and augmented as well. So it's very interesting to see that.
All right. Thank you, Vikash.
Yeah, and I'll chime in a little bit of modeling perspective. I think Vikash and Marek and Sherif, you all laid out the topologies pretty well. So one thing from a modeling perspective that we see as you are planning for this augmentation and what here and how much you need to be adding, a very generic approach that is taken today, you get one degradation curve from the OEM and you basically apply that all across your different augmentation phases. And in reality, what's going to happen is as you add more capacity, that basically means your initial battery that you had, that's going to be operated at a lower C rate now, is going to be operated at a lower depth of discharge. That means the degradation of that initial system is going to slow down. So practically, you basically, as you do augmentation, you end up getting smaller subsystems of your larger systems, and all of them are going to degrade a little bit differently. And you need to be taking that into account along with any forward curves for your battery prices and do a full optimization to really understand at what year, how much you will need to be adding. So that's where we see that current practices is more like rule of thumb. So the OEMs are giving you one generic curves and basically giving you a rule of thumb every 3 year or 5 year, they're coming back and adding capacity. based on the blocks that they offer, which is often not the optimal because they are not looking at it from a lowering the overall cost of ownership. So that's another aspect to take into account as you are planning for these augmentation schedules, because those can be significant as well.
Also, I'll add just one thing really quick. So Marek talked about in the Arabian region, because projects are remote, they're mostly heavily reliant on overbuild strategies because of the high cost of getting back to those sites and adding battery capacity, just the fixed cost of mobilization, demobilization. So for the developers out there and IPPs, that's something to just keep in mind. We've seen a lot of ridiculous proposals for BESS system augmentation. We've seen a lot of proposals for just each year augmenting the system, and it's just as if it's free to go back and add battery capacity. There's no mobilization, demobilization cost, engineering cost. So really just take what you get from technology providers with a grain of salt. And just in general, definitely augmentation planning is one of those things that deserves a lot more attention than it's currently getting. All right, and we'll do one last question, then we'll shift to Q&A. So here, solar plus storage coupling methods. I want to vet here with our panelists. What pros and cons are you seeing for different types of coupling for solar plus storage? There's AC coupling, there's DC coupling, there's DC coupling with solar inverters that are bidirectional. Any feedback on that from our panelists here?
I think historically, more and more, especially in the US, it was a lot of AC coupling, right? Because it was cleaner, it was done, you weren't sure it was an existing solar site, you wanted to add storage to it. So AC coupling was the way things were done. But I see more and more especially in regions like India and so forth, economics plays a strong role, right? You're now with the DC coupling, you can have one unified inverter, one transformer, you're reducing costs, both on the equipment, installation, all of these pieces, right? So I think emerging markets will go more down the DC coupling route, right? And especially when you're planning for a new particular project, right, which involves solar plus storage, which we've also seen some examples in the US where we've seen DC coupled put together when it's a new solar plus storage project, right? But historically, what we've seen is if it's an existing solar site, the complexity of having to replace that inverter and DC couple it is too much, and people just go clean and let's just do AC couple. But yeah, it's a very exciting area, and I think there's a lot of obviously cost benefits that come with DC coupling, but also it's a question of the particular project, and each project is a snowflake, so you need to figure out what makes sense for that particular project and how that's going to work.
Yep, absolutely. I think, go ahead, Robin.
Yeah, I agree with whatever Vikash said. I would just to tag on. The decision to DC or AC couple really depends on the use cases. And then, of course, the market structure. In a market like in the Northeast, in the Northeastern US, in Massachusetts in particular, they have something called the SMART program. And the SMART program actually is structured in a way that incentivizes DC coupling over AC coupling. It's just the structure of the program. And when you're looking at coupling strategies, you have to look at the market, the incentives for a couple, what the incentives are, how that would tie into kind of architectural decisions, and what that means from a performance standpoint. Just to put some kind of pros and cons in context, right? So if you're looking at DC coupled, and I know we're not sharing any slides here, but typically you have a shared inverter, right? For DC coupled projects. The BV and battery share a common DC bus and a single bidirectional piece inverter. The battery charges directly from VV before AC conversion and kind of maximizing kind of clipping capture and low voltage harvesting. But some of the advantages of kind of DC coupling are you have better round trip efficiency at the POI. So you don't have double kind of AC and DC conversion. It typically saves you about 2 to 4% energy loss per cycle. You're able to take advantage of clipping capture where the battery absorbs generation that exceeds the inverter limitation, recovering otherwise what would have been curtailed. And that can materially improve your energy yield, right? Or your kilowatt hour per kilowatt kind of metric. And then it's the simplest single point of control architecture for combined dispatch optimization. Although from a disadvantage standpoint, a single inverter, your inverter can be the single point of failure, right? So if the inverter goes down, the rest of the system also goes down with it. And so there's no system redundancy built in, unfortunately, in that architectural situation. And it's DC, what we find with DC coupling is it's less flexible when it comes to real-time co-optimization with grid signals during high generation periods, right? So if you're in the middle of the day where solar is pumping electrons, and you also want to participate in frequency regulation as an example, then that really becomes a limiting factor. On the flip side, if you look at AC coupling, where you have separate inverters and both connect to the AC bus, you have full grid charging capability that enables you to capture those ancillary service revenues in the midday despite having high generation solar. You have greater system redundancy. The PV side and the BESS could fail independently, and you can still continue servicing the system with the online inverters. It's a simple control architecture. Each system operates with its own EMS logic, reducing kind of the BMS to MPPT interaction complexity. And there's no voltage compatibility constraint between battery and PV, right? For DC coupling architecture, you do require a DC to DC converter, a buck boost converter to levelize the voltage between the battery, the solar, and the PCS. But on the disadvantage side for AC coupling, you have the higher losses. Again, as I mentioned, it's approximately 2 to 4% round trip efficiency penalty versus DC coupling. It's a higher balance of system cost, right? You have to forego any kind of clipping capture, and so your inverter will curtail as needed. And yeah, those are just the pros and cons of each architectural decision there.
Yeah, so definitely that last part on clipped energy. So definitely region specific. So Matic for the Arabian region, a lot of sun. Definitely that must have an impact on how you see this. But I'll pass it over to you. What's your take?
I'll make it quick because there's a different lens. I think the technical aspect was covered really well there and the pros and cons. The biggest issue is actually often the market aspect, because you're right. Technically speaking, there are advantages of DC coupling, especially you get a high yield out of your solar site, right? The fundamental, I don't know if we assume everyone knows what we mean by this, but you can put more panels, right? You can get to a higher inverter loading ratio, so more PV panels behind each inverter, and it's not clipped or wasted anymore because you can store it in the battery if ever the solar panel on the DC side is exceeding the AC capacity to export. So that has a big advantage. But the problem is you have to then essentially have a combined IPP, right? You have to say, I'm not auctioning a solar project, because solar standalone IPP is very straightforward. Investors love it. Very simple, right? You sell energy, no problem. Standalone BESS, a little more complicated still from a financing perspective. Most, let's say, debt finance lenders are still less comfortable with like offtake structures, a long-term PPA for BESS. Combine the two, and it's somewhere in between. It's more risky than just the standalone PV. And you're really then having to ask that the developer takes that risk and wraps it, because the technology provider for ESS is usually pretty clean with an AC scope. When you've got that shared inverter, who's responsible for it? Is it going to come from the PV EPC? Is it going to come from the BESS integrator? It's that gray area, and that's the biggest sort of issue, is that you have to really have someone who's willing to wrap the two technologies together, and an IPP offtake structure that encourages that. So there are places in the world where that's being done, but it's not that common yet. We mostly see standalone solar or standalone BESS IPP, and that's the main. If you look at the region, Middle East, that's mostly what's happening as well. There are, if you look at United Arab Emirates, there is DEWA and EWIC, so the Dubai and basically Abu Dhabi Emirates, respectively, energy companies. One has gone for standalone storage, the other has gone for solar plus storage. So both types are being experimented in the region.
Interesting. All right, we have a lot of questions here, but I'll do my best to try to take some of them here. First one from Shiva Jairam. Short, shallow discharges associated with ancillary services are difficult to accurately quantify during financing stage. In the absence of a well-defined dispatch profile, is it necessary to rely on simplified metrics such as equivalent full cycle counts or energy throughput limits to structure warranty and LTSA requirements? And I'll put that over to Jakir. I know you've been working a lot with Duke University on this very topic. So I'll start with you, Jakir. Go ahead.
Yeah, so I think what he's pointing out is that the ancillary services dispatch really depends on the market condition, and it's very difficult to predict that what that market condition is going to be. So in the absence during the planning phase and financing, if you do not really know how the market condition is going to be, what is a reasonable assumptions to put in? So the problem there is the operating characteristics of ancillary services are much different than these one equivalent full cycles, right? So what there happens is ancillary services, you are doing 5%, 10% very short burst of energy releases, so a lot of shallow cycles compared to these equivalent full cycles where you're going to fully charge the battery completely and then fully discharge it. And that is a very conservative assumptions. So what I would typically recommend is you use the historical data for the ancillary services, and you make sure that the equivalent throughput still remains 1 cycle a day, but you follow the shallow discharge pattern for the sizing.
Yep. And also there are companies out there that predict what these signals are gonna look like. So here in the US, like for example, we're working with Horizons Energy. They're feeding market signal forecasts directly into our platform, but there's many of these companies. I'm not sure if there's equivalent to them in Europe or in the Arabian region.
Yeah, there are, just off the top of my head, Modo Energy, for particularly in Europe, like UK, which was one of the first merchant markets that a lot of like focus on what are the revenues, what are the market trends, and because the data transparency is there. So again, just off the top of my head, there are more.
Perfect. Yep. Great point. Yeah, go ahead, Vikash.
Yeah, I was also going to add that with batteries as well, you can forecast the degradation of the batteries as well. And that's an area that has not been really fully tapped into, mostly because the integrators and the cell suppliers are different folks in a lot of cases. And if the cell manufacturers had better insight into how the batteries were being used, I think real-time forecasting of performance or across its asset life would be something of immense value for asset owners. This is like assuming you're not using it 1 cycle a day as you plan to for 365 cycles in a year, and you're using it for the first year for maybe just 100 cycles, but the second year you want to try to capture some of that and see if you can use it longer, then your degradation could be modeled and more flexible from that standpoint. But that's definitely an area I think if battery suppliers have access, as cell manufacturers have access to the data, you have a right BMS partner who can forecast as well, I think it really has a lot of potential to grow into having more flexible performance guarantees as we evolve in the industry.
Yeah, absolutely. And I have to mention this, even though it's a plug. So we are recognizing that specific point. We're actually giving free access to our platform to the OEMs so that they can build models, and there's no basically cost hurdle between the OEMs conveying, or no cost hurdle for the OEMs to convey to our users how their technologies will exactly perform via building a model. We're basically opening that up, trying to help the industry as much as we can from that perspective, because it is really important. Almost no battery is going to dispatch exactly 1 cycle per day every day of its lifetime, and it does make a huge difference. All right, I think that is it. We're at the bottom of the hour here. This was it was helpful for me. I hope it was as helpful for the audiences here, learning from our esteemed panelists. So thank you, everyone, and appreciate your attention here. Thank you. Bye.
Cool.
Thank you.
Thanks. Bye bye.
Thank you, everyone.
Thank you, everybody.